All right, well, it's 1:45, so I may as well get started. I was telling the last class, which is in here, that normally during the winter, I wear like summer clothes to work, right? Because normally it's sweltering in the buildings. Like back when we used to have class in a real classroom, right? It'd be like 90 degrees in the winter. So anyway, I was telling them that somebody must have heard me complaining about that, right? Finally, they were like, well, fine. If you're going to complain about it for years, we'll turn the heat off. If you had me for class before, you may have noticed, if you spend time thinking about my fashion choices, which are not particularly interesting, I'm always wearing dark clothes all the time. I didn't used to wear dark clothes all the time, so I started working here, and the classrooms are 90 degrees. So if I would wear like my white shirt, it's like boom, it's like I come out of a swimming pool, like I'm terrible, So now I wear all dark clothes to cover up that I'm just sweating the whole time during class, right? And they're like 90-degree classrooms in white science. And usually in here, right? It's like, it's not just hot, it's humid in this place normally, right? Anyway, but now, not only turn off the heat, but like where Hope is sitting, in the last class, somebody was getting snowed on back there. A literal snow coming through the ceiling. So I don't know. Somebody heard me complaining for like a decade about how like hot it is in the classrooms. They're like, fine, we'll let the snow come in and we'll turn off the heat. Anyway, so I apologize that my complaining is now bounced back on you guys, although Cody doesn't seem bothered, so I guess it's all right. All right, so just a quick schedule check real quick. You guys gave me some homework today. I want to take, no, not this day. This one, right? So I'll take whatever questions you have in a second about that. But this is our last day of new material before your exam. So on Friday, we'll do like a formal review, and the review materials are up here on Monday. So there are exam 1 review problems. Those have solutions. Here's the exam I gave last spring if you just want to see what an exam looks like. And then the exam will be on Monday. Also on Monday, you have homework that's just over today. This homework shouldn't take particularly long, but I still want you to turn it in. Just I can't give you feedback before your exam. But if you want feedback on this kind of work, you can always show it to me, right? You can show it to office hours tomorrow, send me an email, whatever. I can give you feedback if you want. The feedback over this homework, though, will be very similar to the feedback over this homework. It's the same kind of problems. So anyway, this homework you gave me today, I'm going to have it graded by Friday. So if you have any issues with that, you can also ask on Friday when we review. Okay, so let me start by asking any questions on the homework you guys just turned in, section 3.1 or 3.2. Yeah, Ben. Yeah. Yeah. Okay, good. So thanks for asking about that. So I got a couple of questions on office hours yesterday. So let's not do the whole thing, but I do want, well, sorry, you didn't ask your question. What was your question about that one? Yeah, just like. Yeah, right. Okay, so let's look at it real quick if I can ever find it. .2, number 14, right? Okay, here. Okay, so this problem had basically 3 parts. They didn't separate it out. So the first was to show or verify that these 2 functions are solutions of this. Anybody have any problem with that? Substituting them in? Okay. So then it wants you to explain why this is now not actually the solution of that D. So what I want you to think about is that I got my days mixed up because we had spring break-ish thing, right? Whatever day we did section 3.1, if you had a solution here and you had a solution here and they were like different enough, right? So we had like e to the t, e to the negative t or whatever, right? Then you are allowed to just do C1 times first solution plus C2 times second solution and you were done. Everybody agree with that? So here they're saying like, hey, you actually can't do that and I want you to explain why. But among other things, they're showing you that something is going wrong here, right? Like, again, if this is a solution, number 1, right? This is a solution. Shouldn't you be able to do C1 times first solution, which is the 1, so the 1 right there, plus C2 times second solution? Shouldn't you be able to do that, And the way you show you can't actually is, so here, to show that's not the general solution, you could just pick values of C1 and C2 that aren't 0. Because if you have a 0, then you get one of the individual ones that we know work. So the easiest thing to do is let C1 be 1, let C2 be 1, plug them in here and see you don't get 0 anymore. Does that make sense to everybody? Like, if this were the solution, then any choice of C1 and C2 would have to work. So pick a value of C1, pick a value of C2, 1 and 1 seems reasonable, so 1 plus t to the half. If you choose that for y and plug it in here, you're not going to get 0 out of it. It won't die down the way, like when you plugged in root t, right, into this dE, it died down to 0, right? Isn't that right? It's supposed to, you know? So anyway, you could do like 2 plus 2 t to the half, 3 plus 5 t to the half, whatever. Anything like that actually will break the dE. So then once you make that observation, like, oh, I mean, this individually works, but I can't do this thing anymore, it breaks it, you know? Then finally the problem is like, well, why'd that break? I thought you were allowed to do that, you know? So we had a result in class, I didn't call it this, but it's the only theorem in the sheet basically, right? We had a theorem in class that said you're allowed to do this, you know, but here it broke. So why is that? Have you contradicted something, right? Like, have you not shown that I was lying to you on Wednesday of last week or whatever? That's what the problem wants you to do. So 3 steps: verify, explain why this thing doesn't work, even though it worked in class on Wednesday, and then explain why we don't break everything, why we don't contradict ourselves. So that's the general structure of the problem. Is everybody okay with that big picture on that problem? So can somebody explain, like, if that's a solution, but then suddenly these guys aren't solutions anymore? How does that not contradict what we did in class? We did, yeah, but in class, yeah, in class we said that basically you could do this, you could do that, and then they should still be solutions. So if you plug them in here, you should still get 0. So why is that not happening this time? And does that mean we were wrong before, you know? I'll take this over here, but the reason this question exists is just to emphasize that anytime you have a theorem, it's only useful in some circumstances. And if you leave that theorem's terrain, then like bad things can happen to you, you know? So for example, this problem here, that theorem we had from class, the thing we were doing in class, it only applied to things like this. Like your dE had to look like that, or you had to be able to make it look like that, you know? Y double prime plus free float, like t stuff can do whatever they want, but then a y prime plus more t stuff y. So in particular, you notice the y double prime is not squared, or it's not inside of a sign or something, right? Y prime is also not squared or cubed. The y is not squared or rooted, whatever, right? So this dE they gave you just doesn't fit the form that we were studying. So if you start just like choosing dE's willy-nilly, you know, like the theorems don't apply to, there's no reason to think the theorems will still hold, you know. That's what the question wants you to think about. So it's just pointing out there are limitations to what we were doing, you know. That's why that question exists. So there's actually no contradiction here. Our original theorem from class didn't claim to say anything about this, you know. There's just like off the radar. So who knows how that behaves? I don't know. And when I say I don't know, I literally don't know. Like this, I don't know how to solve this or whatever, you know. It's not part of the purview of the class or this chapter or anything. Okay, so yeah, so I'll have that graded by Friday. So if you have any further questions, you can always ask on Friday or send me an email or whatever. Okay, so now let's, there we go. Let's dive into sections 3.4 and 3.3. Oh, I don't know why I repeated myself here, right? So sections 3.3 and 3.4, both these are very short, so we're not gonna have to hustle through 2 sections in one day. So to motivate what we're gonna do today, let me hop over here. Okay, so on the board up here in the red, I have a dE from Wednesday of last week. And something you guys know within your homework like 5 or 6 times. I don't know. How do you solve this? Yeah, good. So you do the characteristic equation thing. Everybody agree with that? You do this like 5 or 6 times. And then, yeah, you could, of course, hand this to Wolfram, but now we feel ashamed doing that, wouldn't we? This is like r plus 4, r minus 1, like that or something, right? So anyway, so this is just what we did last week. So then the solution is like this. C1 e to the t plus C2 e to the negative 4t. So this d is within the purview of the section, right? So this theorem just kicks right in. I have a couple of individual solutions, so I can just constant them and add them together. And there's everything. Everybody agree with that? What did last one do? Okay, so that went fine. So now let me give you another differential equation and see what you think about it. Let's see, just the one from the sheet. So let's think about y double prime plus 6y prime plus 9y equals 0. We'll forget about the initial conditions. All right, so I'd make 2 notes to myself, right? There's a typo there. And of course, I wrote it the way I meant it. What's missing here, right? So this should be a 9y. So there's no trick there or something. It's supposed to be a 9y. Okay, anyway, make sure Zoom can still see. Okay. So if I hand this to you, and this is last Wednesday, how do you handle this? Yeah, no difference, right? So you do like this. And now this is like this, right? All right. So R is -3 and then -3 again, I guess, is how you interpret that, right? So now, if you just blindly do what we did last Wednesday, let me show you what you write. C1 e to the -3t plus C2 e to the -3t. And then you'd be like, I'm done, you know? What about that? Does this like hurt to look at, right? Doesn't that offend you? Or what's bad about that? Yeah, like that's the same as that, you know? So once you've written this down, tell me something new here, right? So you're saying constant times e to the -3t plus another constant times e to the -3t, but those are the same. You can just condense those down, right? There's only one meaningful piece of information here, right? But we need 2 meaningful pieces of information, right? Did I agree with that? Like e to the -3t, e to the -3t are identical. They're Wronskian is 0, if you like, from Monday, right? They're not enough, you know? We need something different here. So this is actually section 3.4. We're starting here because it's a little shorter. Section 3.4 just tells you what to do here. So section 3.4 says, if you're in this situation here, how do you create something new right here, like different enough, right? And basically all section 3.4 says is, you go like this. Okay. It turns out that t e to the -3t is another solution of that dE. And of course, t e to the -3t is different enough from e to the -3t, right? So if you check their Wronskian, you get something non-zero. Section 3.4 just says that's it. That's how you handle that. So that's nice. So there's not really any particular wrinkle handling repeated roots of the characteristic equation. Now on the handout, I do have a justification of this just because it's a Wronskian hit from last time. So I'm not going to walk through this. But if you wanted to fully justify this, yeah, here's the theorem, right? The general solution is C1 e to the RT plus, just slap a T there, right? If you wanted to justify that, you'd have to explain why this is a solution. So is this. Whoop. Sorry, get zoom back on here. Explain why this is a solution, explain why this is a solution. And then once you have 2 solutions going, you have to prove the Wronskian is non-zero. Okay? All 3 of those things are fairly straightforward. we already know this is a solution from previous stuff. To show this is a solution, it's just a matter of substituting it and it all dies down. So I'm not going to walk through that. And then the Wronskian, you can ask Wolfram or something, right? Wronskian be non-zero. So anyway, like you're allowed to just slap a T right there and you're done. So that's nice. That's all section 3.4 says, and we're done. The only thing I wanted to point out here is that when you solve something like this, I always could ask you to deal with initial values. So I have these here for some extra practice. But now we're actually done with section 3.4. A nice, so that's pretty quick. Okay, so before we deal with this initial values here, any questions on what this theorem is saying here, how you deal with repeated roots? So again, here's section 3.2. That's why section 3.2 exists, right? Now we have this like theoretical footing to completely justify this right here. So Wronskian all up in your face to justify what we do in this section and in section 3.3. Okay, so now let's deal with the repeated roots. Or sorry, deal with the initial values. Keep that, I guess. Okay, so we solved the DE in general. Now we have to deal with the fact that y0 is 3 and y prime 0 is 0. Right, so this, of course, didn't take either of the data points into account. So how do you take into account that y of 0 is 3 and y prime of 0 is 0? I guess you did this in your homework, right? So what did you do? Yeah, so you basically just substitute in, right? And then see what C1 and C2 have to be, right? So we're going to nail down particular C1 and C2. Let's do that. So y of 0 equals 3. So this is pretty nice, right? 3 equals just C1, is that right? That was easy, right? Y of 0 equals 3, so T is 0, right? A bunch of stuff dies off. Do you agree with that? Okay, so now we have to process the other one. So let's think about what y prime is. Y prime is negative 3 C1 to the negative 3T. And then we got to do product rule, right? So plus, let's deal with the derivative first. Plus minus 3 C2 to negative 3T like that. Did I make any typos there? I did, right? What did after the T? Right here, right? I guess we've learned over the course of 2 class days I can't do the product rule. That seems bad. They really should yank me out of teaching Cap 1, I guess. Was that right now? Okay. So then, right, you again plug in 0. Now you're supposed to get 0. So 0 is the output, and if you plug 0 in, let's see, a bunch of stuff dies off. I get negative 3C1 plus C2, and then this term dies because T is 0, right? Okay, so, you know, we have 2 equations here and 2 unknowns. There's one equation, there's the other one. That system of equations, again, you could go to Wolfram, but we'd feel ashamed, wouldn't we? I don't know. Maybe you guys don't feel ashamed the way I do, but aren't we ashamed? Because we know it's like the first equation is x equals 3, right? That's literally the first thing you type into Wolfram. So we know C1 is 3. So then down here, we have a negative 3 times 3, right? So C2 is 9, all right? Would I agree with that? All right. So then your final solution, you just plug in those C1 and C2 values and you're done. Y equals, what did I say, C of 3. So there you go. So from an infinite family of solutions, you picked out the one where like the initial velocity was 0 and the initial position was 3, if you like. You could have other initial velocities or other initial positions, right? Just that will give you a different choice of C1 and C2. Okay, so that's section 3.4. What happens when your characteristic equation gives you a repeated root? Any questions or comments on that? I feel like you can do this in the homework. If you could do the last homework, you can do this, right? Okay, so that's section 3.4. So now let's move on to section 3.3. And before I do it, let me point out, we can completely handle equation 1, which is this thing, right? This general guy. Constant coefficients, homogeneous, whatever else, right? Second order, linear, blah, 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 right? We can handle that DE if the characteristic equation has real roots. Okay, so of course, quadratic equations, right, don't have to have real roots, you know, real solutions. So let's move on to another example. This y double prime minus 4y prime plus 13y equals 0 guy. Put that up. So that DE, if I just gave it to you cold and said solve that, what would you do? Yeah, do the same thing, right? So you'd say, okay, r squared plus 4r plus 13 is 0. That doesn't look like it factors, right? So off we scurry to the computer, and the computer will tell you that r is 2 plus 3i, 2 minus 3i. Yeah. Oh, is my mouse? Yes. Right. Yeah. Too much stuff going on, right? Okay, so anyway, so you do the thing that we've been doing now, right? And Wolfram tells you this. So if you're just gonna like blindly follow this, you're gonna say, okay, I know what the answer is. Y equals C1 e to the first root, T plus C2 e to the second root, T. You know? Isn't that what you would do? Like, that's what we've been doing, right? So the question is, can you do this? No, you know. Now, from a purely mathematical standpoint, the answer is yes. You can write that down. It makes sense, you know. However, for us, the goal of this chapter is to do spring math systems and circuits and to get actual graphs, right? Can you all graph something like this? Like if this is a 1, that's a 1. I say graph it. You know, or if I ask you, hey, where's the mass in space right now? You say, I don't know, man. Like, what does e to the 2 plus 3i times 1 mean? Right? Everybody agree with that? So anyway, this is useless from like a physical standpoint, although mathematically it makes sense. So section 3.3 says, okay, I can't write this down. So how do I make sense of this? You know? So that's how we're going to finish today and finish all the material for the exam. Just how do you make sense of this? You can't write this down, so what do you write down? Okay, so let me just show you how that goes. Let me just give you the punchline, and then I want to briefly justify why it works because it's a nice top 2. But basically it says this: if the characteristic equation, whoops, bring zoom on. If your characteristic equation has solutions like this, complex solutions, and you'll remember, or not remember, I don't know, from algebra 1 or something, I don't know, your sophomore years in high school, complex solutions come in pairs, right? So if 2 plus 3i is a solution, so is 2 minus 3i, right? They always come in pairs. Then all that matters is the real part and then the imaginary part on the I. So in this example on the board, the 2 is relevant and the 3 is relevant. That's all you need. It turns out that the general solution is like this: C1 e to the real part t times sine times the imaginary part times t, and then the corresponding same thing, but you change the sign to a cos. So it turns out the complex solutions give you trigonometric solutions now instead of purely exponential. I mean, there's still exponentials here, but they're now forced to oscillate because they're attached to trigonometric functions. So that's the punchline. And so I'm going to show you an example. I guess I'll show you this example, right, in a second. But it turns out this is how you make sense of complex solutions. So I want to show you just a brief justification of that, because anytime I can show you that infinite series from Calc 1 or Calc 2 are useful, I show it, okay? Because remember how painful it was to do infinite series in Calc 2? Shouldn't it be worth something to do all that, right? And the answer is, yeah, it's actually worth it because they show up all the time. So I'm not going to walk you through a full proof or something, but I just want to show you how all that stuff you did in Calc 2 is of use here, okay? So the goal right now is to think about this. How would you make sense of something like this? What does that mean, if anything, right? So here I have like e to the 2 plus 3it. What does that mean, you know? So notice, I can separate this into pieces like this. E to the at plus e to the bit, like that, not plus. Times. Do we agree with that? It's just a law of exponents, right? And this, that's fine. Right? Everybody agree with that? And I mean, actually, this e to the bit, what? I could do like this: e to the it to the b power, you know, if I wanted to. Everybody agree with that? And something to a real power, right? This part, that's fine. So really, it's just this, where it's like, I don't know, man, what your emotional reactions, right? So either a frown or a shrug. How are we supposed to do with that, right? So really, if you could just make sense of this, then you could make sense of this original guy. Did I agree with that? Okay, so let me just show you how you make sense of this using just a slight bit of Calc 2. Okay, so here's something from Calc 2. Let's see how fondly you remember this. E raised to a power is sum n equals 0 to infinity. T to the n over n factorial. Remember that? Some of you are nodding. You're probably lying, right? It's been a while, right? That's what it was, right? There's the power series expansion for e to the t, right? So if that's true, then if I stick an I right here, right, e to the it, then now I just have it right there. Right, this is just saying e to the stuff equals. So there's that stuff to the n divided by n factorial. Okay, so we're not going to do much more Calc 2, so I don't want to take up too much of your time with this. But I want to point out that this sum can be split in pieces based on whether this n is even or odd. So I can go 0, 2, 4, 6, 8, and I can go 1, 3, 5, 7, 9, split those two things in pieces, right? Everybody agree I can do that? You know, I can split even odd. So here's what that split looks like. Sum -1 to the n t to the 2n. If there's the even guys, 2n factorial. Basically, when you take I to an even power, I squared is -1, right? So when you're doing even powers, you get something real here, and it's -1 to whatever power you're at. And then plus, if you take I to odd powers, you know, I to odd powers, there's still an I there. So I times I is -1 times another I, there's an I there, right? So odd terms have an imaginary part to them. And then you get -1 to the n minus 1. It doesn't really matter here. But notice these are odd, right? 2 and minus 1 is odd. They're using odd thing. So if you don't understand this equals, it's fine. I'm just saying to you, if you broke this thing into evens and odds, you would get these two separate sums, one of which is still imaginary, one of which is real, though. So if you don't believe this equals, you just take it as a given. Because my point now, to finish up the Calc 2 review, is if you were in a Calc 2 class, this would look familiar to you, as would This. You're like, oh yeah, I know what that is. So all of you who are nodding at this, you remember this, you know. You recognize this? As I look at my notes. Anybody recognize what that is? Do you want to take a guess? No guesses even? Yeah. Oh, that's a good guess. Yeah, this is sine. So if this is sine, what's this one? Yeah. So e to an imaginary power, basically you make sense of that imaginary power by translating it cosine to sine. So this now is much nicer to deal with because you don't have imaginary powers. What does an imaginary power even mean? You know? Well, it means you can translate to not powers using sines and cosines. Now, this, of course, is not a full justification of that theorem I had on the screen a second ago, but it shows you how you can start to make sense of something like this, right? So if you're like, oh man, what does that mean? I don't know, bro, right? But then Calc 2 comes along and says, well, if you use power series, you can get it to not be a power anymore. And now you got to process this a little bit more. If you want to see the rest of it, it's in your book. But basically, you take the power, so it's not a power anymore, and this is much easier to process into something real. So there's a few more steps to fully justify this theorem, but that's the heart of it. There's the Calc 2 of it. Okay, so of course you're not going to have to redo this analysis or something, right? But again, this theorem, which is actually what all of the circuit and spring mass system stuff runs off of, okay? Which I'll explain here in a second. But this theorem lets us model spring mass systems, which means the Calc 2 is what lets us do the physics, right? If we didn't have this, we couldn't do the physics at the end of the chapter. So be grateful for Calc 2, right? No? All right, well, whatever. Okay, share the screen again. Okay, so let's solve that dE using the theorem above. Okay, so as with the first day of this chapter, right? Again, you're not going to recreate all this stuff. You're just going to take the theorem and run with it. So let's take the theorem and run with it. So we already did some of the work, but let me recreate it just so we have a complete record of it. Here's what you write on your paper. R squared minus 4r plus 13, 0. Then Wolfram gives you 2 plus or minus 3i. Then you just like truck your eyes up to this formula here and say, oh, okay, I know what the general solution is. Y equals C1 e to the 2t sine 3t, 2 and 3 are all that matter, plus C2 e to the 2t, change the sign to a cos. That's it. That's what section 3.3 says. That's how you handle complex solutions. Any questions on that example? Okay, so I want you guys to try a couple of homework problems here before we go. Let me make a few closing remarks. First of all, let me just summarize here the entire chapter so far. We're trying to solve that. Solving that reduces down to this quadratic equation. Well, that quadratic equation either has 2 real solutions, 1 real solution, or complex solutions. You know, so there's 3 cases. We now know how to handle all 3 of them, right? No matter what Wolfram spits back at us, we can write down a solution. Everybody see that? Okay, now, in terms of where we're going, we're going to take a break to take an exam, right? But at the end of the chapter, we're going to talk about, among other things, spring mass systems. So you have a mass on a spring. It's moving back and forth, right? So what kind of functions do you think model this? Like would e to the t describe this behavior? trig functions, right? Because it's periodic oscillatory, right? So notice the only time trig popped out was from these complex solutions, right? Do we agree with that? Otherwise, we were writing down e to the 5t. E to the 5t would mean like this, right? Just forever, right? That's not really how spring mass systems work unless you have some sort of external force and a spring that can stretch infinitely long, right? But most spring mass systems are like this. Or maybe they die down over time, you know, whatever, right? There's some sort of oscillatory behavior. And we only get oscillatory behavior here, right? Did I see that? So again, Calc 2 is what spits this out, right? And what lets you model this kind of thing, a mass moving on a spring. So this solution we have on the board here still isn't super realistic because you have oscillatory behavior, but you have e to the 2t. E to the 2t gets huge, right? So e to the 2t attached to a trig function, it's like this. You know, e to 2t is huge, right? Did I see that? So really what we'll get at the end of the chapter is either the exponentials are gone, so you just literally get back and forth forever, or you get decaying exponentials, like e to the negative 2t, okay? If you slap a cosine on e to the negative 2t, you get oscillatory behavior, but then the e to the negative 2t kills it over time. So that's where we're going. So section 3.3 is what we really care about for the end of the chapter. For spring mass systems and circuits, if you watch charge flowing through a circuit, it has the same sort of oscillatory behavior. All right, so let's go to the homework. I guess just try the first couple. I don't remember what the numbers are, but let me just see real quick. You should be able to knock out the first 2 or 3 before we go. I just want to have a chance to talk to you individually, see if you have any issues. So see what you think about 3.3789. See what you think about those first 3. 3.3789.